Hi, my name is David Wayburn and I will be presenting a short PowerPoint slide movie on a replacement for the Prandtl Plus Scaling Parameter Set. This video is a follow-on to the Prandtl Plus Scaling Failure and its remedy video, which was in turn based on an archive.org paper. Today we will discuss the follow-on research presented in another archive.org paper listed here. In this video, we will show the identity of the new parameter set that is intended to replace the Prandtl Plus parameters, and we will lay out the reasons the new set is better. We will start off with a brief summary of where we are so far in terms of inter-region scaling for the turbulent boundary layer velocity profile. There has been a great deal of research whose main objective is to study the scaling parameters that make the scale velocity profile look similar to the scale velocity profile at a downstream position. If you can find these parameters, you now have a pretty good idea what is controlling the physics of the boundary layer flow. Assume we have a bulk flow encountering a thin flat plate. Two velocity profiles are said to be similar if they differ only by a scaling parameter in y and u. Mathematically, this is written as this equation. Normally, we are interested in similarity for all y, but similarity for all y is rarely observed in the turbulent boundary layer. So instead, we will look for similarity in the near wall region. What we are interested in is delta sub s and u sub s for the particular case of the near wall region where viscous effects are important. It has been universally accepted that the Prandtl Plus scaling parameters are the proper scaling for the turbulent boundary layer inner region. The Prandtl velocity scale is given by the friction velocity u sub tau, and the length scaling parameter is the kinematic viscosity divided by the friction velocity. Here is something to keep in mind. The one experimentally accessible parameter that relates the near wall scaling is the wall shear stress, tau sub w. Prandtl had to figure out a way to convert the velocity derivative into a length and velocity scale. His effort was truly inspired. However, his method is not the only way to go from a velocity derivative to a length and velocity scale, as we will see shortly. There are some known problems, but overall the Prandtl Plus scaling has been considered universal for the past 80 years. That is, until recently. In a paper available at archive.org, I showed that the Prandtl Plus scaling has a big problem. If you apply the Prandtl Plus scaling parameters to the Faulkner-Scaon turbulent boundary layer x momentum equation, then the Faulkner-Scaon alpha and beta terms become the expressions shown here. The beta differential equation has a simple solution such that the friction velocity must behave as 1 over x. The problem with this is that the experimental results for Faulkner-Scaon flows do not show this behavior except for the very limited sink flow case. Thus, the Prandtl Plus has a serious problem. This is not a minor problem either, since the Faulkner-Scaon flows are fairly common in the literature. Basically, any wind tunnel experiment involving a flat plate is treated as a Faulkner-Scaon flow, and there are many examples in the literature that fit this category. Okay, so what do we do? How do we fix this? In that earlier paper, I reverse engineered the Prandtl Plus scaling failure and defined a new scaling parameter set, delta sub 0 and u sub 0, that does not suffer the same failure. In a second follow-on paper that we are discussing today, the identity of delta sub 0 and u sub 0 were identified. The key is not the velocity profile, but the second derivative of the velocity profile. The second derivative defines the location where viscous forces are important, which for the turbulent boundary layer is the near wall region. The viscous forces directly influence the wall shear stress and hence the inner region of the turbulent boundary layer. The question becomes, how do we characterize the second derivative profile? To characterize the second derivative profile, we turn to the integral moment method for describing the thickness and shape. To see how the boundary layer integral moment method works, consider laminar 2D boundary layer flow over a thin flat plate. The scale velocity profile looks like this. If we differentiate the profile using the scaled wall normal, we get the first derivative profile. And differentiating again, we get the second derivative profile. The second derivative profile looks just like a Gaussian distribution curve. Probability distribution functions are described using the mathematical integral moment method. The thickness and shape of the PDF function are characterized by moment-based parameters like the mean, the sigma width, the skewness, and the excess. If you want to know more about central moments and moments about zero, check out the Wikipedia page moments followed by mathematical in parentheses. Borrowing from probability methodology, the boundary layer thickness in terms of central moments of the Gaussian second derivative kernel is given by this equation. To make this into a PDF type moment equation, it is necessary to add mu sub 1 and u sub e to normalize lambda 0. The mu sub 1 parameter also happens to be the mean location, the first moment about 0. The flow governing x momentum equation tells us the viscous forces appearing in the momentum balance are directly proportional to the second derivative of the velocity. This moment description is therefore identifying the thickness and shape of the viscous forces contributing to the momentum balance. Thus, the new length scaling parameter has one important advantage over the Prandtl Plus parameter in that it can be directly traced to the physics of the boundary layer. In the Prandtl Plus failure paper, we identified the reverse engineered parameters as delta sub 0 and u sub 0. We now have an identity for the delta sub 0 parameter, and it is the mu sub 1 parameter. The boundary layer mean location is part of a system of boundary layer parameters and kernels. In addition to the second derivative kernel, we also have the interrelated first derivative kernel and its parameters, as well as moments based on the velocity profile directly. More details are provided in the journal paper listed here. We have identified the mean location as the length scaling parameter, but what about the velocity scaling parameter? From the Prandtl Scaling Parameter failure paper, we reverse engineered new scaling parameters by imposing the condition that the ratio must be proportional to the wall shear stress. It is possible to show that this must be the case for similarity. We also just showed that the second derivative moment's mean location is given by this equation. Hence, the appropriate velocity scaling parameter is the velocity at the boundary layer edge, u sub e. Okay, so what are the advantages of the new parameter set? Why should we adopt this set to replace the Prandtl Plus parameter set? Well, first of all, it does not suffer the Faulkner-Sconn theoretical failure problem. Another advantage we already discussed is that the new thickness parameter is part of a moment-based boundary layer description method and can be directly linked to the physics of the boundary layer through the momentum balance equation. The next advantage has to do with whole profile similarity, the case where the profiles look similar over all y. If similarity exists in a set of boundary layer profiles, then it is possible to prove theoretically that the new parameter set must be similarity scaling parameters. The Prandtl Plus parameters have never been shown to be similarity scaling parameters. Now, for the turbulent boundary layer case, this advantage does not apply since whole profile similarity has not been observed for any turbulent boundary layer data set except for a few sink flow cases. However, it is important for the laminar flow case. The two parameter sets are intended to deal with the near wall region where viscous forces are important. In fact, all boundary layer situations fit this definition, including laminar boundary layers. It makes sense then that any near wall scaling parameter intended to scale the viscous forces should therefore also work for this case. For laminar flow, the viscous forces are important through the entire boundary layer region. Therefore, our expectation should be that we will see similarity over the whole profile, not just the near wall region. Here are some experimental CFD simulations for laminar flow on a thin flat plate. These results are new and not included in the archive.org paper. The results are striking. All 7 profiles for the new set show complete overlap, whereas the Prandtl Plus set does not. It is hard to see, but there really are 7 curves on the left taken from 7 locations along the plate. Recall I stated that it is possible to theoretically prove that if similarity is present in a set of velocity profiles, then mu sub 1 and u sub e must be similarity scaling parameters that work. Well, here's the experimental proof. This puts the Prandtl Plus parameter advocates in a difficult situation. They need to explain why the Prandtl Plus do not work very well, but the new set is bang on. The new set is definitely better for laminar flow, but what about the turbulent boundary layer? That is what we started out to study after all. For the turbulent boundary layer, every example I have examined appears to look similar for the two parameter sets. Here are 7 profiles from Scarry and Krogstad. The near wall results appear very similar. Hence, as far as the experimental turbulent boundary layer results go, it appears that they both work equally well. Okay, we are not yet done with the advantages of the new parameter set. The question of what part of the boundary layer the parameter sets work is very important, since we are dealing with partial profile similarity instead of whole profile similarity for the turbulent boundary layer case. So, consider the Prandtl Plus parameters. The fluid flow community has built an elaborate conceptual map of the inner region of the turbulent boundary layer velocity profile. It includes many subregions, with a linear subregion closest to the wall, followed by a buffer subregion, and then the Logarithmic Law subregion. Each subregion supposedly has a fixed location based on a Prandtl Plus value. For example, the logarithmic region supposedly starts at y plus equal to 30. However, this whole subregion culture has no basis in theory. It is all based on suppositional observations of scaled experimental velocity profile curves. There is no theoretical support for these subregions, nor is there experimental support. Advocates talk about the regions as if you can physically measure the thickness and the start and end points of the subregions. You cannot. One of the historical problems with the subregion model is that there is no way to prove these subregions exist, or that the subregions have a fixed start and end location. Instead of an unverifiable model based on speculation, we propose to return to the two-layer model made up of the inner region, where viscous forces are important, and the outer region where they are not. This model can be directly traced to the flow governor equation's momentum balance equation. There are no fixed locations. The dividing locations are based on actual measured thickness values. These thickness values are calculated using the integral moment-based thicknesses. For the viscous region, mu sub 1 and sigma sub v, and for the outer region, m and sigma sub m. These thicknesses are extracted directly from the boundary layer velocity profile. Okay, one final thought. The following are some new results that are not in the paper, but I think are relevant. One of the reasons why there has been so much work done on the Prandtl Plus parameters and the law of the wall is as a way to justify the extraction of the wall shear stress based on the measured experimental velocity profile. The wall shear stress is incredibly difficult to measure, to the point that experimental measurements are rarely attempted in wind tunnels. Velocity profile measurements, on the other hand, are routinely measured. The flow community has been forced to rely on the law of the wall to extract wall shear measurements, even though there has been no theoretical or experimental validation as a law of nature. None. There are various theoretical derivations that indicate the expected interaction of the inner region and the outer region means the velocity profile at the junction between the regions must behave logarithmically, or maybe as a power law. However, we would like to point out that none of the derivations require that the scaling parameters must be the Prandtl Plus parameters. It turns out that it is possible to develop a similar logarithmic function using the new parameters. So, how good is the new log law? Here are some fits to DNS experimental data at different Reynolds numbers. Neither log law correctly predicted the friction velocity. More importantly, the residual plots indicate neither logarithmic function is correctly predicting the velocity profile. I have done a few other comparisons to experimental data, and truthfully, this new log law is probably not as good as the old log law. However, the point is that neither of these so-called log laws are directly supported by a theory that ties in the scaling parameter identity. Okay, that's it. Thanks for tuning in. The results are detailed in a paper available in the link in the description section. Thanks again. Goodbye.